Assalamualaikum and good morning. Today will be our first chapter 2 on flexible retaining wall. So we start the class with looking at our content. So as you can see from the lesson plan, chapter 2 will be on flexible retaining wall. The flexible retaining wall covered for this topic are embedded wall and anchor earth wall. So please remind back some types available for retaining wall. For example, gravity wall, cantilever wall, reinforced soil wall, basement wall, bridge abutment wall, anchor bulkhead and tie-back wall. These are the walls that has been covered in the previous course, such as geotechnique. For this topic, in the chapter 2, these are the contents that you might see later. First, types of flexible walls, modes of failure embedded walls, analysis method of embedded walls, and design standards of embedded walls. Before we can understand the modes of failure, we have to understand what are the types of flexible retaining wall and why we call it as a flexible retaining wall. For your information, the flexible retaining wall can be split into two, which are embedded wall and anchor earth wall. For example, for embedded wall, why it is called embedded wall due to the conditions. For example, here is that and then due to some purpose why we are using the retaining wall. The retaining wall in geotechnical engineering, it is often necessary to prevent lateral soil movement, whether you are using the gravity wall or you are using the brace excavation wall or you are using the cantilever retaining wall. Before you can use the retaining wall as a wall that can prevent from failure, you have to estimate the lateral earth pressure that acting on this structure, which to be able to design them. For embedded wall, some example that we can cover on this chapter is cantilever sheet pile wall, anchor earth wall. You can see from fixed earth support and also from free earth support. Embedded wall, it is installed in undisturbed ground, after which excavation takes place on one side. For example, driven sheet pile, second piles, contiguous piles diagram wall. And the embedded walls act as cantilevers or be provided with single or multiple anchors or props. The cantilever walls, for example, or any embedded walls, you can see in some application in construction. For example, you are going to have a new site project in the existing building. So the next site area to you is a high-rise building. Similarly, on the left and right sides, and then you are in the middle, new site projects. In order to prevent any soil failure underneath few meter deep below ground surface, you have to place in the cantilever. You have to place in the embedded wall so that any construction project can be proceeded without the soil failure. Embedded walls are different from gravity walls in ways, flexural and design structure as simple and prop cantilevers. Their weight is ignored in stability analysis. They depend for support open passive resistance mobilized in the soil. Excavation usually follows installation rather than backfilling. So these are some examples modes of failure of embedded walls. as you can see on the figure here, figure A is referring to the forward rotations of cantilever shaped by wall, while B is a rotation about anchor point, C is an excessive bending in stem, and D is an excessive settlement behind wall, E is a bottom heave, F is a overall slip. So this will be, as you can see on the slope prevention, or we call it slope protection by using the anchor. So let's go to the next content of this chapter 2, which is analysis methods of embedded and anchor earth wall. There is no exact method to design or analyze the complex interaction of excavation depth, wall material stiffness, and passive pressure resistance. So these are the three factors that control to the analysis method and design. The excavation depth, which need to be identified, and the wall material stiffness, whether your wall is made from the steel or concrete, so you have to define or you have to determine the stiffness of the material, and also the passive pressure resistance. The active pressure would likely mobilize behind the wall. With anchor earth wall, there is also anchor geometry and initial anchor with stress. There are four methods of embedded wall analysis. You can use first method as an idealized limiting pressure, second method to analyze by using a simplified approach, third method by using realistic and limiting approach analysis, and the last one is a simplified numerical by beam and spring or by using the computer simulation or computer software. Just refresh back cantilever shaped by walls, the active thrust, passive thrust, and the passive resistance. The cantilever shaped by walls always used as a temporary structures in cohesionless soil, which is the effective cohesion is equal to 0. Look at the phenomena on this figure. Assume the wall in the figure 8.4a will fail by rotating about a point C just above the 2D, in which passive pressure will be developed along BC in front of the wall, along CD behind it. So it says that behind the wall that will be an active pressure at the BC, and along the CD in front of the wall that will be developed a passive pressure. To simplify the analysis, the assumption may be made that the passive resistance along CD here, and in front of wall as a passive resistance, acts as a point load at point C, and the assumed driving depth is a D, which is BC. Thus, the three forces maintain equilibrium at the limit state. For example here, active thrust is a PA is equal to half KA gamma H plus D squared. And then the passive thrust PP is a half KP gamma D squared. So to calculate the passive resistance, R is a PP minus PA, and for equilibrium, you need to take moment at point C. On the pressure diagram at B, this is the theoretical pressure distribution. By using the simplified analysis method, so the pressure diagram being simplified as in the figure 8.4c. So look at to the difference between figure B and C. Here, you can see that below the CD of the wall, which is the passive zone, has been demolished or diminished due to the assumptions to make the analysis simple. So The remaining left to you only the active thrust PA at the back of wall, also PP in front of the wall. So to solve this problem, you have to take the force equation and also the moment equation. So please remember again how to calculate the active thrust PA and also passive thrust PP. The active thrust and the passive thrust by considering the area of the pressure diagram. For example, here behind the wall is the active thrust. So the area of the diagram is a triangle. Therefore, the active thrust is a half times with the pressure in active times with the height. So the height here is a D plus with a H. While for passive thrust in front of wall, the D is equal to the height of the passive pressure diagram. Again, the cantilever sheet pile wall is a temporary structure in cohesionless soil, so it is used only when the height of retained soil is relatively small, around the height 3 to 5 meter. The greater retained height may lead to larger deflection at the top of the wall. Typical failure mode of a cantilever sheet pile wall is by forward rotation about a point near base of wall. Need to be determined embedded depth D needed to ensure stability. So we go to the first method of analysis of cantilever sheet pile wall by using the idealized limiting pressure. So these are some concepts in idealized limiting pressure. You can see that how the active and passive thrust develop behind and in front of the wall. So look at closely. The active and passive thrust are developed similarly at the back and in front of the wall. So by assuming that active pressures acts along the whole back of the wall and assume that the passive pressure acts along the whole front of the wall. And finally, what can we have from the last figure on the right side here? If the entire wall tilts forward by rotating about the point O, then the both passive and active pressure can act on both sides of the wall. So it says that way. So active passive can act in front of wall, similarly at the back of wall. However, the line of actions for active and passive will be different in the front and at the back of wall. So at the back of wall, active pressure above O, while the passive pressure at the below of O. However, at the in front of wall, the passive pressure will act above O and the active pressure will act below the point O. Okay, the idealized profile of the pressure diagram as shown by the solid lines assume the sudden jumps in the profile from active to passive and vice versa. So to make sure the stability of the cantilever sheet pile wall, so we have to take on the horizontal force equilibrium and also the moment equilibrium. Okay, this is the first equation established by considering the horizontal force equilibrium from the figure 1, 2, 3 and 4, and also from the equation 2 by taking the moment equilibrium at O, the rotation occur at O point. So develop the equation 2, and then in order to determine the two unknowns T and Z, we have to use both equation 1 and 2 to solve simultaneously. So you can find the D and Z by substitute the value and using the calculator. Okay, this is how we can solve the example using the idealized limiting pressure. So you have to find first of all the active and passive coefficient laterals. Ka is a 0.33 while Kp is a 3. And then you have to substitute into the force equilibrium equations and substitute into the force equilibrium equation with the simplification. And the next one is that you you simplified again the force equilibrium equation. So the last one remain as a 3 times 5 plus d minus z square plus 27 times 5 plus d square minus 27 5 plus d minus z square is equal to 27 d minus z square plus 3d square minus 3 times d minus z square. And then again, by taking the equation 2, substitute this value into equation 2. So you can have the last one as seen in figure 7. And then do it simultaneously both equations from force equilibrium and the moment equilibrium. Therefore, the D is equal to 4.9 meter and Z is a 0.5 meter. So what is the total penetration depth? So the penetration depth is a 4.9 meter, which is equal to 4.9 meter. The next one, we go to the second method of analysis. The second method of analysis is a simplified soil pressure profile. So just now, first analysis method is a idealized. Second one is a simplified soil pressure profile. So what are the differences between both analysis? At the first one, you can see that the pressure diagram developed at the back and in front wall are quite similar to the idealized limiting pressure approach. But however, it is involved with a simplified soil pressure profile. So when it says to the simplified pressure profile, it means that you can see that the rotating moment taking at C similarly the force equilibrium, and this one you will see that the most significant changes the net passive resistance. So assume that the difference between the passive resistance at the back of the wall and the active pressure at the front acts as a concentrated force R at the two. So here is C. This implies that the net passive resistance below the point O is represented by concentrated force R acting at point C slightly below O. Okay, this is the diagram. So this is what we call it as a net resistance R, which acting at C is not acting at O. So the depth D naught corresponding to the line of action of R can be found by equating moments about C to 0. First, find the lateral thrust or force due to Ka and Kp and their lines of action. And the next one is the depth D naught corresponding to the line of action of R can be found by equating moments about C to 0. And first, find the lateral force and their line of action. And the simplified approach forces you can have this one, for example, PA is a half Ka gamma H plus D naught power 2, PP, RP and PA, and equating moment about C. This is what you have. Okay, this one is an example in order to solve the problem using the simplified soil pressure profile. So this quite easy. I believe that easy because it is a simplified one. Due to some this case is that the moment is acting at the two of wall, it's not acting at the O. Okay, what we can summary from this method is that the approach is very straightforward, suitable for hand calculations. The pressure diagram behind and in front of the wall may appear more complicated if the soil profile has more layers and if there is a groundwater present. However, the basic concept of dealing with the problem are the same. The value of d naught is slightly less than the value of t obtained from the full method and is more likely to be nearer to d minus half z. Hence, we compensate for the smaller value of d naught by increasing d naught by a small amount, about 20%. This 20% increase in d naught is to account for the simplification involved in this approach, and it is not a factor of safety. Okay, one of the example question for theoretically, what you need to understand or to memorize on the differences between the ranking theory and also the column as pressure theory. For example, the ranking theory is the principle of the plastic equilibrium of the strained soil, and it is infinite failure surface, while column derived according to the principle of force equilibrium, only one failure surface. Okay, just one example of theory, but there's a lot chances or there's a lot of opportunities theoretical can be asked in the test and also in the final assessment. Okay, let's proceed to the third analysis method using the realistic soil pressure profile. So this is specifically in the passive zone. Okay, what you can see from here is that just now, the idealized limiting pressure profile as shown in the figure 1 here. So we have active at the top of O, and we have passive below of O at the back of wall, while in front of wall we have oppositely positioned with passive acting above O and the active acting below O. This is the soil pressure in front of wall. And then in this method analysis for realistic soil pressure profile, there is no sudden change in the pressure profile at the depth of O where the wall rotation takes place. You can see here the full solid line black. For idealized, there is no black line. But in the realistic soil pressure, we have to take it, but that is not so realistic. Why? Because you might see that actually the pressure just acting just stop at O. But then we, in order to analyze it, we take it the full black line here from the top of retaining wall in the active zone behind wall, and then from this one we meet to the next active pressure in front of wall. We connect it and then we close it at the back of wall. So it means that it's cover both, but then when you see closely, the solid black lines is not so realistic to represent the soil pressure. A more realistic net pressure diagram is shown by the red solid line below. So this is what produced after the realistic conditions. So the net passive pressure profile below the excavation level is typically non-linear. For analysis purpose, can idealize as a piecewise linear profile as shown in the next slides. So this is what the simplification from non-linear as pressure diagram. The dash red line is a non-linear, but then we assume as a linear pressure profile. So consider the linearized net pressure diagram. Y and Z are unknowns. So you see that here? We can have the Z. Also, we can have the Y. Where is the Y? Y is the height from the toe of wall to the point A, where Z is the height from toe of wall to O. Need to find Y in order to obtain the required wall penetration. This approach is the same as before. Find the value of Y required to achieve the length of the wall by using the force and moment equilibrium. So at this point A, assuming that the pressure P is equal to 0, so all this one is a pressure. So PP2 is a passive pressure, PP1 is also a passive pressure. So C is equal to gamma Kp minus Ka. So we have the Ka, we have the Kp, and then we have some also uh, the simplified of coefficient lateral pressure by Kp minus Ka. So you solve by replace all forces above A by a single force resultant Ra, so that the Ya can be found as here, last equation. Then to calculate Z, we make use of the horizontal equilibrium. Ra plus these diagrams go to 0. So take it part by part. So Ra plus PP2 plus PP3 times Z over 2. So this is the distributed pressure diagram from here in the Z zone, in the Z height. It's like a triangle. So Z over 2 times with the PP2 plus PP1 plus PP2. So then minus with a small purple shaded area here, and solve the equation 1 in Z and Y. Take it the moment equation 2 equilibriumly, and by similarly the equation 1, or substitute equation 1 into equation 2, that produce to you 4th degree equation in Y. So in order to find the required depth of penetration, we have to add Y plus A, because we want to calculate what is the penetration depth of the cantilever sheet-wall wall. In a summary of solution steps, this is the simple guide you can follow. First, sketch the given conditions. Compute the active and passive aspiration coefficients Ka and Kp. Compute the constant C, the pressure Pa1 and Pp, the resultant pressure Ra and its location Ya. Insert the values from step 3 into the 4th degree equation and compute Y. And the last one, required penetration is Y plus A, and the total required length of wall is a H plus Y plus A. Okay, this is an example of the realistic soil pressure profile. So similar case, similar soil conditions. Then now we have the D, and we also have the Z. You draw the pressure profile diagram. Then you calculate the pressure active. You calculate the C. You find the A, and then you get the resultant thrust here. Find the YA, and calculate the passive pressure and then find the YA and A. As before, the presence of more layers of soils, especially in the upper part of the wall or groundwater table, can be complicated. Accordingly, the values of RA, YA, and PP would be affected. The overall 4-degree equation is still valid if the soil embankment region is assumed uniform, and can still substitute the modified values of RA, YA, and PP into the equation and solve for Y. Okay, just now is the case for realistic. So we have covered almost 3 methods of analysis. So now we go to the example how to solve the problem using analysis method number 3. So first of all, when you analyze the problem, you have to see what's exactly methods of analysis you need to use, and then the profile of the soil with a cantilever sheet by wall. In some cases, there's some assumptions that you need to consider. For example, here, so you are given the site of excavation is 2.25 meter deep in the sand, to be supported by cantilever sheet by wall. The water table being 1.25 meter below the bottom of the excavation. The unit weight of sand above the water table is a 17 kilonewton per cube meter, and below the water table, the saturated unit weight is a 20 kilonewton per cube meter. These are the characteristic parameters of the soil, allowing for surcharge pressure of 10 kPa on the surface. Determine the required depth of embankment of the piling to ensure a factor of safety 2 with respect to gross precipitate resistance. Check that the rotational and translational limit state will be satisfied for the above embankment depth using partial factors. So the B part ni is considered in the design section. Okay, as you can see here, when you calculate after you have the soil parameters 35 degree and delta is a 0, what is the delta here? Delta here is a soil structure interactions. So we assume as a 0, the Ka is 0.27 and Kp is 3.7. So the information is given the saturated unit weight and unit weight of the sand. To allow for possible over-excavation, the soil level should be reduced by 10% of the retained height. So thus, what the height of the wall you can get from here is 2.5 meter. And the water table will be 1 meter below this level. So what the final diagram of this problem, you see here, this is the retained soil is 2.5, and then 1 meter from ground surface where it is start the water table effect. And the next one, we have the surcharge on the top of the net side. And also we have, due to the analysis being done using the realistic soil pressure profile, so you have the resultant R, and this resultant R force is acting at the C, at the toe of the wall. Okay, first you have to draw the pressure diagram. What we can have from here is pressure diagram 1, 2, 3, and 4. And 1, 2, 3, 4 is the active pressure diagram, while 5, 6, 7 is a passive pressure diagram. So flashback how to calculate the pressure diagram, active and passive. So consider the once you get the pressure diagram is equal to the Ka times effective vertical pressure, or we call it Ka times with the effective overburden pressure, while passive pressure diagram is Kp times with the effective overburden pressure. Okay, in order to calculate the area or we call it as a force. Force is equal to area of the diagram. For example, here, figure diagram 1 is a square. So the pressure diagram is a Ka times effective over burden pressure due to surcharge 10 kPa times with the height of the retained soil. So the force for pressure diagram 1 is a 0.27 is a Ka times with the 10 is the effective over burden pressure times with the D plus 3.5. And then arm means that it's a perpendicular distance where the force acts from the point C. That's why here we have the half D is from here plus with 3.5 over 2. What is the moment? Moment is the force time with the arm. So look at closely how to get the force and arm. Similarly, moment for all pressure diagrams from 1 to 7. Next, okay, by taking the force and moment about C equal to 0, this is the final equation left to you. By trial, the solution, the D is a 2.75 meter. So the required depth of embankment is a 4.75. And finally, the D is equal 2.75. So what is a D? D is vertical distance that we measured below the water table to the point C. And you have to check the force R evaluated and compare with the net passive resistance with the additional 20% embankment depth. So the R is a 74 kilonewton. And the passive pressure acts on the back of wall between 6.25 and 7 meter. At the depth of 6.625, the net passive pressure is given almost 600 kPa. So the final one, we can see that the net passive resistance is a 427 kilonewton, which the R or our 427 kilonewton is larger than the R. So the force acting is only 74 kilonewton, but the net passive resistance is 427 kilonewton. So it is satisfactory. So the next one is the simplified numerical approach. When you say the simplified numerical approach, you can use taking the beam behavior or taking the spring behavior. Okay, this is how you can solve for cohesionless using the soil spring to find the YA and YP, while for cohesive soil using the springs to get the YA and YP, and also the simplified numerical approach by using the computer calculation or computer simulations. So these are the some parameters input in the software, and then how we can prescribe the excavation stage in the SPW. So you can set here by starting off the loading step 0. Then you increase loading step to 1, excavated site, and then loading step 1 right, but now on the retained earth site. Okay, what's produced to you is this one. So because in the computer simulations just now, we want to simulate the real site condition for excavations by assign different excavation stage or different loading step. So first of all, when you set the loading step equal to 0, that is during the initial conditions. Then when we want to simulate the excavations process on site, so we set or we assign loading step 1 as a left side as excavated site for soil 1, and then we assign that for the loading step 1 on the right side here as a unexcavated soil, or we call it as a retained earth site. So you get all the inputs for the soil 1, soil 2 for different loading step. In the computer simulations, using the software, the most crucial importance is that uh, when you assign for the input parameters that represent properties for each soil, also the assigning loading conditions, for example here is a loading step 1 and loading step 0, so that the results produced from the computer simulation is similar to the calculation you made using difference analysis. Okay, this is the force and the moment produced to you using the SPW. Okay, the next one we go to the design standards and embankment walls. There are three standards can be applied in. First, using the British standard. The next one is using the Eurocode 7, and the last one is a gross pressure method. So this some kinds short input informations when you use different methods of standard. For example, here when you use the British standard, a surcharge with a 10 kPa plus 20% of embedded depth and 10% of future unplanned. And for Eurocode 7, geo-limit state using the design approach 1 with a 10% future unplanned excavation. And for gross pressure method, using the simplified pressure diagram. Why we call it as a simplified pressure diagram, we have to ensure that at this time, the moment will be taking at the two of wall. Okay, now we try to solve this problem just now with the different standards of method. First, using the BS, second one using the Eurocode 7, and the last one is using gross pressure method. Okay, for example, when you use the British standard, it notes that the minimum design surcharge of 10 kPa. So there's a specific clause that you have to follow. And then the future unplanned excavations of 10% of clear height in the front of wall. So you have to fulfill this requirement. And then, so it says that when you analyze that, this is 10% of clear height in the front of wall. So that the D is counting from here. D from the red dash line to the toe of the wall. And we have the Z. Okay. Next one, you calculate the Ka and Kp. And then you draw the earth pressure distribution. Okay, we have the active zone. We also have the passive zone. Okay. Again, we have the D node, we have the D, we have the clearance cap of height is 10%. So the next one is that find or determine the earth pressure for all the pressure diagrams here for active and passive zone. And then you calculate the forces acting on wall. And then consider moments about O. Okay, consider moment about O. Okay, sorry. Here you have to take moment at O. Okay, it's not at the toe of wall. So when you take the moment at O, so there will be difference at the level arm. For example, here, moment. What is the AC is a anti-clockwise. C is a clockwise. So when you consider moment at O, some force might act in a clockwise direction and other might act in the anti-clockwise directions. So the significant anti-clockwise and clockwise direction will be on the sign, whether you have a positive sign or negative sign. So you set the assumption first, your rotation moment in which direction will be positive. For example, here, clockwise moment is a positive and anti-clockwise moment is a negative. So the sign is very important to indicate to you whether it's carry the positive or negative. And then get the total force here. Use the both equation 1 and 2 simultaneously to determine the D naught and the D. Okay, if you're using the simplified pressure method, okay, the simplified pressure method, you can see that now we are taking moment at the top of the wall. So this pressure diagram also being simplified. So if you make comparison from idealized pressure method with a simplified pressure method diagram, that will be the straightforward to be solved here. And then since there is no double layers and there is no water table, so the analysis or the design will be more simplified. So what we have from here that the D is equal to uh, 1.2 D naught and the final D we can get 8.4 meter. So when you do the simultaneously equation, cubic equation in D naught, you can get that the D naught is a 6.98 meter, force is a 568 kilonewton. To obtain the design depth D, the value of D naught is increased by an amount equal to the extent required to generate a net passive resistant force below the point of rotation at least as large as R. So we have to check the net passive resistance. This demands additional calculation and it is common practice to avoid this by increasing D naught by 20% to give D. So in order to get the final last D, we take it the 1.2 D naught. So that what we have here, the D is equal to 8.4. So remember just now before we start the analysis design, we assume that the 10% unclear excavation. So when the last stage of the design, we have to increase back with the determine the final value of D. So the next using the standard method of Eurocode 7 with a geo-limit state with a design approach 1. Okay, it is note that for future unplanned excavation of 10% of clear height in front of wall and no explicit requirement on surcharge loading. So there's no loading here. And again, 10% of clear height in front of wall. Okay, by using the Eurocode 7 geo-limit state design approach 1, design approach 1 means that combination 1, the partial factor sets A1 plus M1 plus R1. So we have to take on the material properties as for example here, gamma G, disturbing, these kinds of the parameters value. And then the earth pressure distribution, we take at the O. So you can see that this one pressure distribution similar to the previous one. And then the next considerations that you have to consider in the Eurocode 7 is the design action. So design action here is similar to the active thrust. So the active thrust PA1, PA2 due to the earth pressure is a permanent. So we consider as an unfavorable action. So this is what you have from the design action in the Eurocode 7 geolimit. And also in the design actions, how to consider the how to consider the passive earth pressure. So one view is that the thrust produced by earth pressure should be treated as an end action and therefore multiplied by gamma F to obtain the design value. Another is to treat active earth pressure as an action and passive earth pressure as resistance, in which case the latter should be divided by gamma RE to obtain the design value. Okay, these some assumptions for design action, design limit, and so on will be specifically explained again in the next chapter 3. Okay, the next effect actions in Eurocode. So the next effect of action is like you consider the resolving the moment and the force equilibriums. So substitute or simultaneously solve the equation 1 and 2 by using the combination 1 method. We can have the D naught is a 5.2 and the minimum depth of embedment D is a 5.7. If we use the combination 2 with the partial safety factors, so the minimum depth is a 6.6 while the D naught is a 5.7 meter. So last but not least here, by using the standard method of gross pressure. So the gross pressure is using the simplified pressure diagram where the force and the moment is taken at the 2 of wall by consider the factor of safety is 2. So the safety factor of 2 is a substitute in the passive pressure diagram. So look at here, the pressure diagram, 3 times 2, 3 is a passive coefficient, times 2 times G naught divided by 2. 2 is a factor of safety. Okay, consider moments about O. O at the 2 of wall. So we have the active force, so 3.33 times G naught plus 5 power 2. And passive force is 15 D naught power 2. And these are the lever arms. So equating clockwise and anti-clockwise moments. So the final D is 9.24. So I think that I have finished for chapter 2, flexible retaining wall for cantilever sheet pile wall. And if you have any questions, please do PM me, and don't forget to do your ODL activity for this week. And thank you.